there's a whole collection of things that you should have in your notes. And should you not, let's make sure that you and I match up with what I think you should have in your notes, okay? Let's talk first about the basic motion equations. And I'm going to say that these are the generic versions, meaning they apply to all oscillators, and it's up to us to know what the controlling factor is on those oscillators. So for example, the basic motion equations are going to be for x, v, and a. One for position, one for velocity, and one for acceleration. The position one should be x naught, and if we haven't fully defined these, I'll define what each of the variables is in just a minute, times the cosine of omega t. Then our next one is going to be minus x naught omega times the sine of omega t. And the last one is minus x naught omega squared times the cosine of omega t. Those are the three motion equations that go with simple harmonic motion. So we have motion equations for things that have a constant acceleration, and now I have ones that have a restoring force. Now, I don't want to bring this up, but I saw it in passing yesterday when I was going through some practice materials. You can write all of these with the opposite signs, and they're all okay. And when I say signs, I mean opposite trig functions, and they'll all be okay. So you could have started with sine and not cosine, and that would be fine. That would still be considered a motion equation. You need to know why we defined one of these versus the other. We defined this one based on cosine because on the spring you pull it out and you let it go. So we started with an initial displacement. But it is acceptable to have all of it in the reverse, and it still works just fine. And as evidence for this, I would say, look at the graphs you already have produced. None of them started perfectly at cosine or sine. They all started somewhere in the middle. What's important is that you know the difference between the way cosine works and sine works. And if you don't, it's okay. I'm going to try and show you that a little bit today. But these are the basic motion equations. Then there's some things that go along with that. First, omega is angular frequency. Generally, it controls your oscillator. It controls the timing of your oscillator. This is going to be some kind of physical parameter. It's going to have stuff in it like mass and spring constant and length of your string and center of mass of the system. It's going to have all sorts of stuff in it, but it's going to have information about the physical characteristics of your oscillator. So whenever you're approaching something like this, I want to just give you some overarching ideas that always work. First, this is almost always going to be some kind of fraction. We already know for the spring mass that it's K over M. And it's always going to have a square root in it like this. So you can assume it will always have some kind of square root. The bottom is always going to be about the restoring force. Sorry, I said bottom, but I wrote it on top. The top is always going to be about the restoring force. It's going to have something in it about what's causing the system to go back to equilibrium. The bottom is always going to be about inertia. This will always be true. So no matter what kind of oscillator we talk about, the top will be about something dealing with the restoring force, and the bottom will be about something that deals with the inertia of the system. This will always be true. For the spring mass, we know it's K over M. And we're going to have like 2 or 3 others that go along with that. Who'd you have to give it to?
Rui.
Okay. Next, x naught. The x naught in this function represents either the initial or the maximum displacement. You'll notice it's out front of a trig function. And I know for a lot of you, your trig functions are a little bit elusive to you, but it's always going to be in the units of whatever it is you're measuring. So for your lab yesterday, it was centimeters or meters. But for the pendulum, it was radians, because it represents whatever is displacing. And so for your pendulum, you're measuring angles, right? It was displacing with an angular displacement. But for the spring mass, there was a linear displacement. So all oscillators are displacing something, but it's going to be whatever the displacement is of your system. So while this represents where the object is at any one time, this represents as far as it's going to move in one direction or the other. Now, because these are all trig functions, all of them have this portion. All those things we just learned, or I just wrote down, all the things we learned yesterday and the day before, can you tell me how much this would compress the spring, what's the maximum compression in the spring, and how long till it comes to rest? I'll give you like 2 to 5 minutes and see if you can come up with the answers. What the capabilities are. Question A was from first semester. Could be solved from first semester. Because right now, what kind of energy does the block have before it hits the spring? What kind of energy is it going to have when it comes to rest against the spring? I guess less information there, but I can only teach stuff so many times, but it's going to have elastic potential energy, right? You could have done this as a straightforward conservation of energy question with 1/2 mv squared equals 1/2 kx squared. In fact, let's start that way. If I start that way, I get 1/2 mv squared. That's what I have right now. That has to equal 1/2 kx naught squared, because it's going to be the maximum displacement. And we're looking for x naught. So I'll cancel the 1/2, divide by k, and then take the square root. Well, we've done this problem lots of times. But I also know something else. And again, trying to get you guys to move to something new. Let's just slide this over here for just a minute. V equals minus x naught omega sine omega t. Right? This is the maximum velocity. So V equals x naught times omega. Omega is the square root of k over m for a spring mass oscillator. So we'll solve this for x naught, and I'll get the square root of m over k times v. This tells me the velocity at any time, but I didn't need that. So I don't need the whole thing. I just need the part that's about the maximum. But there's no reason you couldn't do it this way. We did that all first semester. Plugging your numbers in, least interesting part, so I'm not going to go through that. We good to go on to the next one? What?
Is there a reason why we couldn't have done Hooke's law or something?
Perfectly good reason why we couldn't have done Hooke's law. Because we weren't asked anything about the force. And the force was changing the whole time. So it wouldn't help us there. You know, Hooke's law tells us about the force. We could use it maybe to find the acceleration. But as the motion equation goes, that's not going to work out for us because the acceleration is changing the whole time. That's why we had to go through all this complicated stuff just to figure out what the motion equations were. Ready to go for the next question? Or do you have more to ask about this? All right, let's do the next question. The next question I asked you, how long does it take till it comes to rest? We know something about the length of time to do things here. because we know that once the box is connected to the spring, it is a simple harmonic oscillator, right? It's a spring mass oscillator. In fact, specifically just now, we said the period would be equal to 2 pi divided by omega. However, we don't want a whole period here. A whole period is how long it takes to do one complete oscillation. How much of a period are we actually looking for? Not 1/2, 1/4. Look at your chart. From maximum velocity to stopped is 1/4 of an oscillation. Just look at the chart, make sure. Right? That's why we did that. That's why I made you write the chart, made you write in t equals 0, t equals 1/4, t equals 1/2. So going from maximum velocity to fully compressed is 1/4 of the period. So a lot of you got the period, but you didn't get what I asked. Okay? How about we try another one? I think we need some practice. I'm going to go with the same level of difficulty. All right, so I have a little spring launcher from my box. I'm going to pull the box back against the spring launcher 0.5 meters. Then I'm going to let it go. So question A, how fast will the box leave? Question B, how long does the launch take? You can see that I'm asking the same question, right? Just different numbers. Give it another shot. So I pull it back 1/2 meter, let it go. How fast will the box leave? How long does the launch take? Give it a shot. I'm going to start with how fast will the box leave? I'm not going to use conservation of energy. I'm going to use the fact that I know V max has to equal x naught times omega. And that this omega is a spring mass oscillator, so that's the square root of k over m. I'm going to go right from there because that's this unit. I could do conservation of energy and that would work just fine. I'm just choosing to do it this way. Same stuff. So V max is going to be x naught, which looks to be 0.5, times the square root of k, 400, over m, 3. Any question about that? Plug in your numbers, get whatever. Question B, how long does the launch take? Well, this is another quarter period launch. I'm going from maximum displacement to equilibrium, and that takes 1/4 of the period. So I'm looking for a time which is equal to 1/4 of the period. But the period is 2 pi divided by omega, which makes this 1/4 times 2 pi times square root of m over k. Same numbers, same stuff. All right? Time to change. Need something different now. You did the same problem twice. Let's try something different. Not going to change it much, just enough. I want to design a clock that uses this same spring, 400 newtons per meter. I want it to oscillate once every second so I can use it as a clock. What mass should I use? That's it. That's my only question. I'm going to ask a follow-up to it, but that's my only question so far. Same spring. I want to create a system that I know will oscillate once per second. What mass should I use? How's that flow state working for you?
If I'm correct,
So did anybody else get 10?
Yeah.
I got 10. Did you guys get 10? Would you like to work it out? Why are you doing this? All right. What did I give you in this problem?
Okay.
What's that? I did give you K. What else did I give you? I didn't give the displacement at all, actually. I gave either the period or the frequency, depending on how you look at it. I said it's going to make 1 oscillation per second, which means 1 second per oscillation. So it doesn't matter really which one of them you use, but the answer is going to be 1. I used the period function, which is 2 pi over omega, or 2 pi times the square root of m over k. And it says once per second. So 1 second per oscillation. That's it. So if you didn't do this, phooey on you. If you did do this and didn't get 10, that means your arithmetic's bad. So it could be arithmetic. Ready for another one? All right. Got to change it up a little bit. Okay. Your parents finally say okay and they buy you a trampoline for the backyard. First thing you do is you grab your little 20-kilogram brother and throw him on there. He's not actually jumping on there. He's just bouncing up and down on it. Before he's actually left the mat, he's bouncing up and down 3 times per second. What is the effective spring constant of the trampoline? This is the exact same question you just performed, but I'll say it all over again. You chuck your little brother on there, and he's kind of bouncing on there, and he bounces 3 times per second. What's the effective spring constant of the trampoline? Converse real fast. I gave you the frequency, 3 oscillations per second, so that's 3 hertz. Right, the number of times they bounce per second, and that equals 1 over 2 pi times the square root of k over m. Check your work, because some of you did this different. I got a much bigger number than almost everybody told me. Try this at home tonight.